Now we're going to listen to Stena, one of our sponsors to Donsö Shipping Meet. And one company in Stena is the Battery Loop. And they work together with DNV Sweden. And the heading of this speak here will be Electrifying the Maritime Sector. The EU-funded Sea Lion project evaluates and maps out innovative ideas and sustainable solutions to boost electrification of the maritime sector. And this project, it looks at the potential bottlenecks and lack of availability of shore power by using grid-connected energy storage system in ports to complement shore power installation. So, I will welcome from DNV Sweden, the team leader and power system engineer Lucas Tomé, and from the Battery Loop, from the Stena company, energy analyst Anders Graal. Welcome.
Yeah, thank you for having us. So my name is Lucas, and this is Anders. And as Petronella introduced, we'll talk about the Sea Lion project. So it's a co-founded project from the Connecting Europe facility of the European Union. But before we go into details about the project itself, we'll talk a bit about the global energy transition. So as you're well aware, we're currently in a big global energy transition. There's increased electricity and energy need on the consumption side and also on the production side. And this is across all sectors of all industries. But there's two specific sectors that are hard to abate, that there's specific challenges, and that's the aviation sector and, of course, the maritime sector. But for the maritime sector, the International Maritime Organization has set a target to reduce emissions by 50% by 2050 from a 2008 baseline. And this will be managed primarily by energy efficiency, but also significantly changing the fuel mix in the maritime sector. And of course, electricity is one major part of this. So apart from the maritime sector, in Sweden, we also have a big increase in electricity need. So in about until 2050, we'll see approximately a doubled increase in energy need. And also if we look a bit closer to home, also in the port of Gothenburg, there's about a 3 times power need foreseen in the same time period. So yeah, there's a lot happening on the consumption side, globally and also locally as well.
And the consumption of electricity, one part of it, we need to have a grid that are dimension for that usage, but we also have a huge transition in how we produce the electricity. And here's one example of things that drive the demand for energy storage system in the grid. And here is every line is 1 hour, and the one round on this clock is 1 year. And this is in Sweden, the production. And we have the blue that is nuclear power. And as you see, it goes with the same power every hour, almost the year around. And we have now a huge demand for new electricity, and the main source that will be installed in Sweden in the coming 10 years will be wind power. And as you see, the wind power has another type of production curve. Some hours we produce really lot energy with the wind power, but hours in between, and some days for a couple of days we have low production, and this drives the demand for energy storage systems in the net. And this is also an opportunity to be able to have flexibility in the usage, so we use more electricity when we have low prices and high production from wind, and we also have the capacity to reduce the electricity consumption hours in between. And that can be hard if you, for example, drive a ferry and you have time slots where you are in port.
So we have changes in nature, both on the consumption side and production side. And of course, yeah, volatility and electricity prices and so on. So that leads us to this Sea Lion project. And the main partners of the Sea Lion project are Port of Gothenburg, Port of Kiel, DNV, Battery Loop, Stena, who is also leading this project, and Stena Recycling as well. So as was introduced before, the project partners have come together to map out innovative ideas and sustainable solutions to boost the electrification of the maritime sector using lithium-ion batteries. And the basic idea is that you could have battery storage in ports to complement the charging of potential future electric ferries or also other sources of electricity need in the ports. So you can charge it over a longer time, and then over a short period of time you can discharge the battery. So that will decrease the need for high power capacity need in the grid connection, and also use for flexibility in the power grid. So the Sea Lion project specifically looks at the feasibility and also the potential investment of 2 large energy storage systems to be located in specifically ports of Gothenburg and Kiel. And the Sea Lion project, it's a 2-year project. It's ending the end of this month, so it's already been going for 2 years. And the project has looked into several main activities. So the first one was looking at the potential design of an energy storage system. And a part of this activity was also looking at the energy and capacity need in the ports to do energy audits that Anders will talk a bit more about later on. In this activity, we also looked at the safety and security of energy storage systems in ports, so similar to what the previous speaker was talking about, but now on shore rather than on ships. The second activity is looking at the evaluation of the recycling potential of lithium-ion batteries. Third one is looking at the assessment of grid impact, so what impact will these batteries have on the grid, and also what support can they provide to the grid. And lastly, looking at the business case for a port electricity storage system.
So what we first did was that we looked into the harbors and mapped out how does the electricity, how is it used in the harbors today. And what we see is that a harbor is not an electricity-intense site. You have the quay lights maybe and buildings that use electricity. You have some maybe some heating or cooling, but overall it's not a power-intense site. What drives need for power in the harbor is when you connect the ships, the vessels to the grid, and you have this shore connection. And that has been in Göteborg for many years, but throughout Europe, shore connection isn't that common. And when we start to connect the vessels for just the local need of electricity, when the vessels are in quay, we drive up the electricity usage high compared to the other port. And that's also depending on what kind of route, how many hours is the vessel connected, and what's the need for electricity on the vessel. What's further on is going to happen at these sites is that the tug masters that operates in the area will need electricity, for they will in many places be driven by batteries. We have also both trucks and cars that arrives to those harbors that want to charge at this location. And also when the vessels are going to be hybrid, or like for example the Stena Line Electra ferry that will operate between Sweden and Fredrikshamn, full electric, then there will be need for power to also be able to charge the vessel itself. And if that's a short connection time, the power demand will be high, and that's a huge opportunity to have an energy storage system at the quayside. So what we did was that we mapped those harbors. We looked into the future, what will happen, and we also designed a couple of energy storage systems that will be suitable for the different use cases that we saw. And it's mapping between the power demand, but also what kind of energy demand will that be. So the energy demand is how many batteries do we need, and the power demand is how we convert the DC in the batteries to AC. And we have also many other things that we include in the design, like how to cool the batteries, and how to make it modular and scalable, and how to install it in the harbor. And a battery is not just a battery, it's a system with many things included. We have the battery here on this corner side, but we have the inverter that makes the DC in the batteries to AC, and we have transformer to get the right voltage to the connection point. We also have all the safety systems with door sensors and the climate control, fire detection and suppression. And the thing is that this system needs to be clever to also find out when to charge and discharge according to demands from real estate buildings or charging. There can also be local production from solar or wind at the site. And this is the head of the system. That's a local controller and a cloud service, so we can schedule the battery for the right things at right time.
And one important aspect of the design is also the safety and security and risks of a battery storage system. So we conducted 2 workshops, one together with RISE, where we looked at the hazard identification, and we focused on these external events that was talked about also from the previous speaker, on the internal events, such as an internal fire, and also external, that could be fire, collision, weather and environmental impact, and also grid impact and human error. And during this first workshop that we did the end of last year, we identified at least 22 current safety measures that were in place, but also about 37 potential safety measures that could be implemented to even increase the safety and reduce the risks further. As a part of this, we also looked at the safety, operation, and performance of grid-connected energy storage systems. We looked at battery fire, off-gassing, and explosion risk, and also specifically at the cybersecurity of an energy storage system. We also conducted a workshop just a week ago together with the local fire and rescue service, so Räddningstjänsten Storgöteborg, where we asked for their input and their perspectives on this potentially large-scale battery storage system in ports. Because as also the previous speaker mentioned, I mean, knowledge is really important. So even though this potential energy storage is quite far ahead in the future, it's important to start early and identify these risks and the potential hazards so you can implement safe measures beforehand to reduce the risks. So moving on, it's been a 2-year project. We've covered a lot of areas. So one of this was also looking at the grid impact assessment. And here we looked specifically at the grid stability and also the ancillary services. So apart from just being used to charge the ship, we could also have the energy storage system provide stability to the grid. So we looked at several different ancillary services, such as frequency support. So that's mainly to be used for fast frequency restoration and also frequency containment reserves. We also looked at peak shifting, peak shaving for energy arbitrage, and also flexibility markets. So for example, there's a local flexibility market already started here in Gothenburg, which is called Effekthandel West. We also looked a bit on voltage support and harmonics. So yeah, in conclusion, you could say that there's a lot of potential stability that the power, or sorry, that the energy storage system can provide to the grid. One interesting thing we also looked at is grid island operation, and this I would say is probably more, let's say, in the news at the moment with the, let's say, the invasion of Russia, and also where you could have an external, let's say, party impacting the electricity grid, and eventually or potentially this could lead to a complete blackout of the Swedish grid. And one idea is then to create electrical islands so that you could have large cities such as Gothenburg and Kiel operate in an electrical island. And a battery storage system of this size is very crucial in such a system to provide stability and support. So that, yeah, that's also something we looked into quite a lot.
What about the business case also? The energy storage system is like a multi-tool where we can use it for local services and to supply the ship with more power. And we have the delivery point to the grid owner where we measure the output of electricity, and we pay both the price for the amount of energy that we use hour per hour, but we also have fees that depends on the highest amount of energy we take during 1 hour, and that's the power tariff. So when we have the battery in between the connection point and the ferry, then we can peak shave. So if we are the grid owner, we don't see the huge peak because we take parts of the peak from the battery. And if we look from the vessel, then we have the battery as a power boost instead. So part of the day we charge the battery from the net, and when we connect the ferry, we take power from the net, but also from the battery, and together they charge the ferry with the right amount of power. And this is also a very important thing about the business case, is that we have service stacking, that we are able to do local services at the quayside, but also deliver services to the local grid and also to the whole grid, this synchronous area that is the whole Nordics here in Sweden. So one example here for one of the sites that we were calculating, it was a huge energy storage system with multiple containers of batteries with the right inverter power. So the installed energy was about 25 megawatt hours, and the power was 20 megawatts. And that's an investment cost for around 40 million euros. And as you see, the reduced power cost is one thing that we see as a benefit, that we pay less to the grid owner because we have less power from the grid, but also we have potential to revenues for those stabilizing services that we provide when the ship isn't in the harbor. So in this case, it was a good investment to supply the ferry with power from the grid and from a battery. And this is also a thing for the grid owner, that if we don't use that much amount of power, there is also possibilities to connect more producers to the net in the local area, that we can connect more buildings, more companies, more industries if we don't book up a high power.
All right, thank you all for listening. We'll be standing by a roll-up by the Stena stand later on, so you can approach us if you have any further questions. And please do.
Yeah.
Thank you.
Thank you.
Thank you so much. What do you think is the biggest success factors in this project?
Well, for me, it's been the collaboration between the different parties. I mean, we've had the main project participants, so yeah, the
Yes.
ports, DNV, battery loop, and also Stena. So we have the manufacturer and also the, let's say, the power system aspect, and also the operational aspect. So that's been great. And we've also been able to collaborate with RISE, so the Research Institute,
Yes.
to further expand our own knowledge and also the grid owner itself. So yeah, it's been a lot, and also Räddningstjänsten. So to get all these different perspectives into one project has been
So the collaboration is really the thing.
yes,
Yes.
definitely.
What do you say?
Yeah, I totally agree. It has been a new product and much knowledge that we have earned together. For our side in Battery Loop, we are a startup inside of the Stena sphere, and we do those energy storage system. And for us, this project has been very valuable knowledge about how to make good products to stabilize the grid. And we have not this large system, but we have systems that operates right now in the grid. So yeah, those 2 years have much has happened, and much will happen the coming years also.
Of course. And now we have been taking part of this knowledge. What more do you do to reach out with the result?
Well, all the reports and our appendices and so on will be publicly available as well. But yeah, we also had communication through video interviews and so on that was done. So yeah, there's a lot of information, and we do have our own website as well that you can check out.
And as you said, if you want to meet you more and speak and discuss, you can reach you in the stand.
Yep,
Where?
just over there, the
Yeah.
Stena,
Over there.
Stena stand.
The Stena stand.
We'll move our roll up over there as well, so you can easily find us.
And we represent parts of the project, and there are many more people here from the project. Yeah, take your time and discuss this with us if you think it's interesting. Yeah.
Thank you so much, Lukas Tomé and Anders Gahl.
Thank you.
Thank you.